Yes.
So welcome everybody, and welcome to this course on many-body physics, which in the beginning here, I just wanted to give you some kind of basic messages of where you find the material. Most of you have been studying here before, so you know roughly where everything is. But I just wanted to point to some specific things. So this is the official website. For those taking other courses which I teach, you will actually see basically the same setup. You will find the information on Canvas. You will find the same information as a weekly email. And you will also find it as a message on the official website. So you will typically see something like this, plans for the week. And I will normally send a weekly email to everybody. And then the material is then something you will find in the GitHub address, and I'm just going to point to where you find the different things. And I guess everybody's familiar with a provider like GitHub or GitLab or similar ones. And the other site for information is on Canvas. So the kind of weekly announcement will be here. You will find a link to videos of lectures. So every lecture will be recorded. If you cannot be in person, you can always attend via Zoom, or you can watch the lecture afterwards. So hopefully that allows you, in case you cannot be here or you're traveling or by other reasons cannot be there, you can always catch up. Okay, so the other thing is actually the GitHub address of the course. And there you will essentially find all the information. I'm still updating my big lecture note thing. So this is something which is work under construction. But you will find, if you click on a doc folder here, you will then find things like exercises. And this week we have a set of exercises. So the exercises are labeled according to the week. So you will find them as both LaTeX files and PDF files. There will be changes to later weeks, but the week 34 is basically set, and that is essentially a reminder of linear algebra, which I will actually do now in the first part of the lecture, just give you quite a quick reminder of the essential linear algebra elements which we need in this course. So quantum mechanics is essentially linear algebra. And then if you go back to the doc folder, you will find my lecture notes, but then there is a list of textbooks. So some of them are actually out of print, but one which we will use in the beginning is this book by Sabo and Östlund, which has a very nice introduction and a nice reminder on linear algebra properties, which are used in quantum mechanics. And it also has a nice introduction to some of the basic ingredients which we need. So this is essentially chapter 1 and 2, which we will cover during the first 2 weeks here. So chapters 1 and 2 give you essentially the kind of introductory material, which I will also present in the lectures. And then there is a book by Shavit and Bartlett, which brings in more second quantization and different many-body methods. And then there are also other textbooks which you can look up as references. There are many textbooks by Springer. This is actually a Springer text. And many of these texts actually can be downloaded for free, as many of you know. So this is a book on theoretical mathematical physics and density functional theory. And some of you may be interested in that as well. And then if you go back to the link here, you will find the link to the midterm exams. So we're going to have 2 midterms, and each of them counts 30% of the grade. And then we have a final oral examination, which we often have tailored so that you can, in a way, reuse what you did during the midterms, and you can make a presentation based on the results from the midterms and also some of the other theories. So it's actually basically set what you will present at the final one. So, and then we will have questions. So typically your presentation will be something like 25, 30 minutes. And then the two midterms, they obviously cover the theory which we have gone through. And there will be a mix of numerical exercises and paper and pencil exercises. The folder, which is called Pub here, this is where you will find the weekly material. But you will also find that linked. So the weekly material, if you go to the official website, you have this schedule site. And what you will find then when you look at the material here, you will typically find a link to the lecture slides for that specific week. So you can always look at the material which we will cover, but you will also get an email with a link to the material. So hopefully there are enough ways you can retrieve the information for a given week. The Zoom link is also presented here. So that's going to be this same Zoom link for the rest of the semester. The exercise sessions will not be recorded. And these are meant more as, and there's no need to hand them in, but they are meant to illustrate the theory we cover weekly. And they also, some of the exercises are exercises which are useful for the midterms as well. So some of you are taking the PhD variant. There is no difference between the PhD variant and the Master of Science variant. There should be. So if those of you doing a PhD would like to have more stuff into the, yes, there's a great. I'm just teasing you. Okay. So the, if we go back a little bit to this website here, if you then look into week 34, you will find both a PDF version of the slides. There's an HTML and then there's a Jupyter notebook. So this week there are, by obvious reasons, no codes which we're going to run. So it's just going to be theory. Feel free to use this material as you want, and you also know that when you have the material here, you can clone it to your own laptops and either fork it and use it as your own lecture notes, or you can just take my updates, because I come with weekly updates typically. And I have an exercise set this week, which is essentially linear algebra. And you will find most of the answers in the slides for this week. And else, I mean, the whole thing with the exercise session is also to discuss and deepen your insights. And Ruben, who is is a PhD in particle physics. So, oh, by the way, before I say that, you know that you can subscribe to these activities. So you can get a warning then if you subscribe to them, whether there are specific changes. Okay. And Ruben is the other teacher here, and he's doing a PhD in particle physics. And he's an expert on quantum field theory. So this course actually has a lot of the same formalism, which you will encounter if you take a course in quantum field theory, except that we don't deal with relativistic systems here. We will mainly stay with non-relativistic quantum mechanics, but you can reformulate everything, whether you want to do relativistic or non-relativistic formalism, by a quantum field theoretical formalism for second quantization, which we will come back to. Any questions so far? So if you take quantum field theory, or you've taken quantum field theory, you will recognize many of the same ingredients which we cover here. Okay, so what I'm going to do now is actually to switch over to these slides. So let me just find them here. Oops, I'll do that one. So I'm going to go a little bit quickly through some of this stuff. And then we're going to dive into the more technicalities, which we need to introduce in order to be able to run calculations here. But in the beginning, there is actually a lot of repetition on linear algebra. And some of this is just a repetition of what we said before. So today we are going to look at some, or remind ourselves about some basic linear algebra. By the way, if you spot typos or things which are missing, just send me a message and I will correct immediately. And the videos will be added afterwards. So the lecture material, as I said, is these slides and the textbook by Sabo and Oslo, chapter 1 and 2. So the idea, as you've probably seen, is to give you an introduction to the quantum mechanics of many particles. Many of the things which we do here, some of you may have taken a course in quantum computing. Has anyone done that? So quantum computing uses essentially the same ingredients. And what you will see now is that we are going to remind you of orthonormal basis sets. We are going to look at unitary operators, Hermitian matrices, just a quick reminder of that. So the kind of computational basis states which we end up with, the whole way of thinking is also something which you would typically reuse if you take a course on quantum computing. So there's basically no difference. And many of the operators which we look at, how you do measurements, quantum mechanical quantities like spectral decomposition of operators, which some of you may have encountered, these are actually quantities and methods and parts of the formalism which apply to essentially any course in quantum mechanics. So what we are going to look at is a set of systems which apply to, since we're doing non-relativistic quantum mechanics, so many of you are doing condensed matter physics, and in condensed matter physics, these are basically standard methods for describing many particles. If you're doing studying quantum technologies, systems like sets of quantum dots, which are confined electrons in layers between semiconductors, they can actually be used to manipulate these systems, and then you would have isolated electrons in each well, and they can be used to actually realize quantum gates and make quantum computations with real devices. So that's one of the typical applications. Condensed matter, I said, atomic and molecular, which is often translated into quantum chemistry. So there's a kind of a long history behind that, because in physics is a field which often moves very much by fashions. And in the 50s and 60s, particle physics was the big thing, and it still is. And people felt that atomic physics and chemistry and molecular physics were well understood. So we leave the details to the chemists. So chemistry, in a way, is just the physics of reactions, in a certain sense. It's not only that. There's much more to the picture than meets the eye. But so atomic physics and molecular physics often migrated to departments of chemistry and developed into what's called quantum chemistry. And in quantum chemistry, there's been a huge theoretical development. And we have an excellent group at the Department of Chemistry with a center of excellence. They're actually world leading, and it's called the Hjorth-Jensen Center. So Hjorth was a Norwegian physicist who actually was among the central people who developed the variational principle in quantum mechanics, and was the first person who ran calculations on the helium atom in the 20s. He actually did calculations with this kind of handheld machines where you could diagonalize up to 12 by 12 matrices. It was quite impressive. Mechanical devices. So you have in quantum chemistry, you have in nuclear physics, lots of these activities going on in material science. So a theoretical understanding of many of these many-body systems is actually central in order to understand, for instance, if you do nuclear physics, why visible matter is stable. Now, one of the things which you will see, and this is, so I'm trying to give you more this kind of overarching picture of things. There are very few systems which can be solved analytically beyond two particles. unless you have some simplified Hamiltonians, which allows you for separation of variables so that you can find analytical solution. So these systems are very few, which means that the methods which we deal with, they represent different types of algorithmic implementations. And then there is often a very short way from that to numerical calculations and numerical realizations. But we obviously need to go through the theory. Many of these methods, you start with a differential equation, which is the Schrödinger equation for many particles. But this equation is an equation you can rewrite in many ways mathematically. So the different many-body methods, they do represent different mathematical algorithms. So one of the algorithms you will encounter is something which is called the full configuration interaction theory, which essentially is you diagonalizing a Hamiltonian matrix. That is one of the many-body methods. And that's a many-body method of choice if you can diagonalize. But you quickly reach, and this is one of the things I will expose for you again and again, you quickly reach the dimensionality you can handle. So in principle, the Hilbert space is infinite. The actual space which you have is normally a little bit smaller, but not small enough for exact diagonalization. So this is an approximation. And full configuration interaction theory has also different names. If you go to atomic physics, it was often called the shell model, and the same in nuclear physics. But the kind of method, this method is normally called full configuration interaction theory, because every way you can realize a set of state is called a configuration. And these configurations are interacting, as you will see later, when you set up the Hamiltonian matrix. So that is diagonalization. That's a plain eigenvalue problem. Then we have something which is called Green's function theory, which technically means that you're rewriting Schrödinger's equation in terms of a matrix inversion problem. So you're taking the differential equation, and some of you may have encountered something like the resolvent in mathematics. And that's something which you can then, it's actually rewrite of the Schrödinger equation where you're solving the inverse problem. You can rewrite everything as coupled differential equations, or you can rewrite it as coupled partial differential equations. But there you quickly hit the wall, because when you solve differential equations for more than 2 to 3 particles, you have too many degrees of freedom, because you have to discretize your integration area as well. So the different types of methods, like also many-body perturbation theory. Perturbation theory is nothing but a Taylor expansion around an energy. So you have matrix inversions, matrix diagonalization, you have coupled differential equations, you have Taylor expansions, but you can also have other methods like couple cluster theory or Hartree-Fock theory or density functional theory, which in practice is nothing but you solving a set of coupled nonlinear equations in the unknown quantities. So this is yet another mathematical recipe. And then finally, one of the very popular recipes, which we do not cover here, is Monte Carlo methods. And Monte Carlo methods is actually you dealing with expectation values and handling an integral in a stochastic way. So this is a whole jungle of methods, and people will obviously fight each other who has the best method. But we are going to expose to you 2 different methods so that you can see the pros and cons. And then clearly, depending on the field you work in, there are some methods which are more interesting to use and others which are less interesting. So if you're just targeting the lowest lying state, which we call the ground state of a many-body system, then methods like Monte Carlo methods, Hartree-Fock theory, or coupled cluster theory, all these types of methods are very good. If you want excited states, then you would typically deal with full-scale diagonalization, which is very limited in a certain sense due to the dimensionality of the matrices you can diagonalize. So typically, the state of the art today by iterative methods, so there's a whole set of mathematical methods called Krylov methods. And for symmetric matrices, there's a subset of that, which is called Langsow's method. These are solved iteratively. And you can then tackle dimensionalities of around 10 billions of basic states. Beyond that, I mean, it's you're hitting the wall. Okay, any questions so far? So I'm just trying to give you the kind of broader picture so that you can see the different things which we are going to cover. So the intro chapter here has some basic definitions. We are going to discuss, to a very large extent, we will discuss systems of fermions. So I know that some of you come from mathematics and you may not be fully familiar with that. So fermions means that the total wave function has to be antisymmetric. So this is a theorem by Pauli, or an ansatz by Pauli, which has not been violated experimentally. And then we have systems of bosons, which are particles with integer spin values, where the total wave function is symmetric. But we will have a focus on fermionic systems because these are often those which are which people are mostly interested in condensed matter physics and in atomic or quantum chemistry, also nuclear physics. But we've had a huge field, which is called quantum liquids, and studies of, for instance, Bose-Einstein condensation. So this is also a topic, if you're interested, we can try to discuss that as well. And that's a topic which has led to tons of Nobel Prizes in physics. We are going to look at some definitions. I'm just listing here different things which we will go through in the beginning, just to have everybody on the same ground. We are also going to jump into what's called second quantization, which is a kind of anomaly as a name, because it gives you a feeling that there is a first quantization or perhaps a third quantization or whatever. So I'm going to use something which is called the number representation. So essentially what it means is that you transform away the spatial degrees of freedom. And you simply look at how many particles occupy a specific state. And that leads to a formalism which is very compact and extremely useful. And for fermionic systems, when you encode it, you can actually encode it in a very straight way using Boolean algebra. Because for fermions, a single particle slot can be either occupied or not. So you would just suffice with a binary set of systems with bits 1 and 0. And there are many different kind of things which we discuss, which are also useful if you are going to take a course in quantum computing. Because in quantum computing, there's something which is called the Suzuki-Trott approximation. There is also an important relation for the exponentials of operators, because these operators do not necessarily commute. And then there's a very important formula which translates into many body methods, which is called the Baker-Campbell-Hausdorff formula. And we are going to see examples of this throughout the semester. So when I write 1B, 2B, and 3B, that means one body operators acting on one particle at a time. Two body operators, it's just like if you think of the gravitational force, it acts supposedly between two planets, for instance. That would be an example of a two-body force, three-body forces, etc. So we don't have real three-body forces. These are often effective three-body forces. And these are mostly of interest to people doing nuclear physics. So you often translate in physics to an effective Hilbert space, which means effective degrees of freedom. So in a certain sense, all of science which you do is finding the relevant effective degrees of freedom. And then coupling them with a more fundamental theory, if you believe in a fundamental theory. And then based on that one, to have a proper mathematical link with them. So if you're doing nuclear physics, I mean, the appropriate theory is something which is called quantum chromodynamics in terms of quarks and gluons. But these degrees of freedom is something because quarks are not frozen out. So they would stay within protons and neutrons, which are the actual degrees of freedom for low energy nuclear physics, for instance, or low energy particle physics. And then you need a theoretical construction where you relate the formal underlying fundamental theory, which is quantum chromodynamics, with an effective theory for, let's say, a low energy system like a nucleus at low energies. And that means that you can, since you are having a fundamental theory, when you translate that one into an effective one, that can produce effective forces, which you then need to include in your formalism. This was just a kind of small digression, but when you see things like free body forces, this applies also if somebody, is there somebody here doing material science? So in material science, when you're using molecular dynamics, then you often need to include a free body interaction. And this is a kind of effective way of representing specific degrees of freedom. So sometimes you introduce this in an ad hoc way. If you're lucky, you can actually have a rigorous mathematical link between a fundamental theory and the effective theory. But just keep in mind that all of science is actually you finding the right effective degrees of freedom. And then you want to link different degrees of freedom in a rigorous mathematical way, which is not always the case. So I mentioned molecular dynamics. So is anyone here familiar with molecular dynamics? Now, molecular dynamics is actually you freezing out the quantum mechanical degrees of freedom and then finding an effective interaction between, let's say, atoms in a lattice. So if you're looking at, let's say, a specific mineral structure or a material, the atoms or the molecules are often located in a kind of lattice structure. And then you need some kind of interaction between the different atoms because you want to simulate the properties of the system. But you have too many degrees of freedom to be able to use the methods we discuss here. And that means that you freeze out the quantum mechanical degrees of freedom and you try to find an effective potential between the atoms, which you then can use in a standard Newtonian calculation, where you have where you solve coupled equations for the different atoms, but using Newton's law of motion. And then you need a force between them. And often what you find then is that you would need a more complicated one than just a two-body interaction. That doesn't describe well the data. And then you can add some phenomenological forces. But there, it's often difficult to relate that to the more fundamental approach. So that would be an example where you don't have a very rigorous mathematical link. In some theories, you can do that, in others not. So there's also a lot of phenomenology in many body physics. And for you guys, sometimes it takes some time to see the wood for the trees, because I've been doing this for, 40 years, which means that you have an ingrown way of speaking about systems in a jargon. So I need to demystify that as well. And some people will always give you the impression that their method is the best possible one. So if people say that, be suspicious. So these are some basic things. This would be our first method. And one technology which is often used in many body physics is very much inspired by Feynman and so-called Feynman diagrams. So that gives you a very compact way to visualize and set up physical processes. It doesn't mean that physics is given by a Feynman diagram. Some people think that. But the Feynman diagram is just a representation of an approximation. So we are going also to look at mean field theories. So how many of you have touched upon something called density functional theory? Yeah, so density functional theory is something which we will also discuss a little bit. And that's very much linked with Hartree-Fock theory. So we are going to derive Hartree-Fock theory, and then we will link that also with density functional theory, although this is not the main focus here because we have an explicit course which covers density functional theory. So that's just to avoid credit overlap. But we are going to link to it. And one of the examples which we are going to look at, some of you may have encountered the electron gas. So we're actually going to, this is one of the few systems where you can find analytical solutions to a Hartree-Fock problem. So, and we are going to cover those details. So the electron gas is actually an infinite system of electrons which see a uniform background by the ions surrounding the system. So you make an approximation that the background is just a uniformly smeared positive charge. And these electrons define an infinite system. And this is a system which has, I should almost say, persecuted many body physicists for ages, because it's a system where many of these many-body methods actually fail at given densities. And the kind of standard benchmark method, what is seen as the answer, is normally based on Monte Carlo methods, and in particular diffusion Monte Carlo methods. And they provide the most exact answer to many body methods. And the other ones are often approximations which don't include all degrees of freedom. And these are things which we will also discuss. But the electron gas is also a system which has been extremely useful in explaining the conductive properties of metals. And that's why we're going to look at it as well. So we have mean field theories. We will cover some many-body perturbation theory, which is a standard method. It's a Taylor expansion around an energy. We will also discuss copper cluster theory if we have time, which is a set of non-linear coupled equations. And if we get some time, I will also say something about Green's functions, which is a very popular many-body method, which in a certain sense is the one which links best with quantum field theory. But we will put less emphasis on it because many of you come from either quantum chemistry or from fields in physics where Green's functions are less used. But if you come from material science, this is a very important method. Monte Carlo method is actually covered by this course. And also we have quantum computing algorithms which are covered by this other course. So I just mentioned this where you find the literature. This is about practicalities, 2 projects, quick repetition of that. We have 4 lectures per week. Everything is recorded, etc., etc. So what I want to do now is to give you all a very quick reminder of linear algebra and some notations here. I will use slides here, but then I'm going to dive into the whiteboard afterwards. But some of these things are things which you have seen. You can just revisit it, just to remind yourself about some basic properties, which we are going to use again and again. So I will always use objects, so we assume that they are complex. In some cases, you have systems like the harmonic oscillator, where you have you can actually rewrite the solution just in terms of real numbers, but you can also rewrite it in terms of complex numbers. You can do that. But the basic assumption is that we have complex vectors and complex matrices. That's the basic assumption. So these are just some notations which I'm going to use. And I guess you're pretty familiar with these notations. So I can go quickly through that. You can always revisit it. So just a quick reminder of notation which we will not use. But we are going to use what's normally called a Dirac notation. But essentially the Dirac notation is just this guy here for a vector. And where you have the given components, in case we have a complex vector, we define the Hermitian conjugate. Sometimes I may be a little bit sloppy when I lecture, as I will mix transpose with Hermitian conjugate, but you should be able to understand from the context, because sometimes your mind is elsewhere and you say transpose instead of Hermitian conjugate. And Hermitian conjugate is a little bit more difficult to say. Okay, but from the context, you should be able to understand. And then you have the inner product in this notation. And then in some few slides here, you will see it in the Dirac notation, which is the one we will use. So this course here has often been attended also by people who have not taken a formal course in quantum mechanics. And what is confusing for you if you're only taking a course like Physics 2 140 is actually the Dirac notation, because more the formal parts of the mathematical aspects of quantum mechanics are covered in, let's say, the second course in quantum mechanics. Like here in Oslo, it's Physics 3-110, which many of you may have taken. Or if you're taking a course in quantum computing in the Department of Mathematics, you would have seen something similar. But essentially, the kind of quantities we deal with are quantities which we will rewrite slightly. Yeah, this is just to remind you about some properties here. And instead of orthogonal matrices, we will normally deal with unitary matrices. Okay? As I said here, the Hermitian conjugate of a matrix is obtained by taking the complex conjugate of each element and then taking the transpose. And often I will just say the transpose or just the conjugate. But hopefully from the context, it's understandable what I mean. Okay, so the longest phrase here is actually the correct one, but then we are humans and we try to shorten things. So another thing which people tend to forget about is the outer product between two vectors. That's also a quantity which is going to be extremely important here, because it's going to define projection operators. So one technique which we will use again and again is the application of projection operators to a specific state, because we are looking after effective degrees of freedom. So you have this infinite Hilbert space of realizations of states, and then you want to project out from that space to a smaller space, and that is the normally introduced by so-called projection operators, which means that you want to develop a theory in terms of these different operators so that you can link this degrees of freedom which you leave out. So just keep this in mind, because I will now reintroduce it. So a matrix, a general matrix is like that. This is also a type of notation which I will use. So I will often just use a matrix in terms of the column vectors. Okay? Any questions? Too obvious? Or I think it's always good to refresh things. And I know that many of you are taking the course on machine learning at the same time, and you probably had to revisit some linear algebra as well. And this is the inverse, and where I is the unitary matrix. And this is also very important properties of many of the matrices which we are going to deal. Yeah, I'm going to go quickly through this. You can look this up, actually. These are properties of matrices. And then we have some famous matrices. And in our case, we often, when we perform these transformations with the projection operators, if we are lucky, we can transform a matrix into a tridiagonal matrix, which is, so you have a full matrix if you're thinking of the diagonalization part. So one of the standard algorithms is something which is called Householder's algorithm, which somebody may have heard of, which transforms a full matrix, a dense matrix. In our case, the matrix is symmetric and quadratic. So when the type of matrices you will encounter are of that type, which means also that when you transform it by Householder transformation, you can get a tridiagonal matrix, and it's easier to find the eigenvalues by iterative schemes. This algorithm, which I mentioned, called the Langsos algorithm, is an algorithm where you reconstruct the full tridiagonal matrix. So a standard brute force way is to take the dense matrix and then perform a Householder transformation, and you get a tridiagonal matrix, and then you try to find the eigenvalues by some iterative scheme, or simply using brute force schemes like Jacobi rotations. But then, if you have a too large matrix, this becomes infeasible. And what you would do then is actually to construct the full tridiagonal matrix iteratively. And that is what Langsos method does. And then if somebody gave you the magic Householder transformation of a 1 billion times the 1 billion matrix, you could transform the tridiagonal back to the full dense matrix, which you don't want to do. Okay. So Yeah, I'm going to skip some of these slides, but obviously you can actually look this up. This has some properties in linear algebra which you have probably encountered, and I'm going to skip these things here. But now I want to extend to quantum mechanics, and this is a notation which we will use throughout the semester, which many of you probably have seen, but there's an equality sign here, so the vector is now going to be rewritten in the standard quantum mechanical Dirac notation. So this is called the bracket notation, which many of you have encountered. Has everybody seen that before? Yeah, I know, not everybody. But this is a standard notation which we use. So just think of, so this is why I want to stress in the beginning here, just to give you a reminder of some linear algebra elements, because at the end, it is just a question of notation. And you can choose to keep that notation here, the standard one you would see in any textbook in linear algebra, or this kind of physics notation which is being used. Because the reason why you have that is that it just gives you a compact way of setting up the expressions for mathematical expectation values. So you always try to find a kind of compact notation. So this is again part one of the jargon, right? But if you just think of the equivalence here, this is just, if you do that, then it should be easy to translate. And then the inner product looks like this. And then you have a general inner product, which looks like that. But that's the same you would have gotten if you had used the other formalism. The thing which sometimes is a little bit confusing, let me just, I have some examples here. These are also things you can look up a little bit, but this is just manipulations of the fact that like these inner products are always a real number. Just keep that in mind. But that for two different vectors, this relation here is in general not equal. And there is an example in the slides here which shows you that that is in general not the same. So these two guys here, xy and yx, may not be the same. So you will see that in the next slide. There are also some other simple relations here, which I just remind you of, because I'm going to use them in the next lecture in manipulating expressions for expectation values. And then in this example here, you will see that this is the inner product. But then if you take this example and you calculate the outer product, you will see that they are not the same. But the relation at the end here is the important one. So I hope it's not too boring, but I think it's always good to remind ourselves about things. And also since I know that from experience that not everybody has taken a formal course, the first formal course in quantum mechanics. And then the outer product actually looks like this. So this is the way you would write the outer product then. And I'm putting the asterisk just to indicate that now we are dealing with complex objects. And the outer product is something which is going to play an important role here. And this is something we will see after the break. So I'm going to set up some simple examples here. And this is our first encounter of a specific system. It's a system which we would call a two-level system. I'm putting this up deliberately because if you've taken a course in quantum computing, you will see that this is also the way you represent a qubit, which could be a realization of a spin-up or spin-down state, but it could be any two-level system. So you have two levels, that is your full space, and you represent one level by this phi 0 and the other by phi 1. So if this is your world, then these two states define a complete set of basis states. And I'm going to put a name on this, which I will use again and again. And I will call this a computational basis. Or just sloppily, a reference basis, or just basis. The assumption is always that the basis is orthogonal and normalized. And we will then use this acronym ONB, orthogonalized or orthonormal basis. So when you, as a small digression before we take a break, if you do quantum computing, one of the things you're always looking after are physical states, and this is a difficult thing, where you can identify two well-defined states. Now, in principle, this system has an infinity of states. But what you're hoping for is that these two well-defined states in the spectrum of a system, could be the ground state and an excited state, that these are states you can use as your only computational basis. And then you can neglect all the other degrees of freedom. So the big problem in quantum computing, the physical realization, is that sometimes you can have thermal excitations when you heat up the system, which means that you can get a mixing of higher lying states, and that spoils your idealized world. And that leads to noise in quantum circuits, in quantum gates, which then spoil the whole calculation for you, or the whole experimentation. So that's one of the reasons why actual implementations of quantum gates are systems which are cooled down to almost 0 Kelvin, because then you avoid thermal excitations. So to cool down a computer to almost 0 Kelvin is not a very sustainable computation from an energy point of view. So when people are trying to shape these quantum gates, they're often looking for materials which have well-identified states, which you then can use as a computational basis. So here, this is just an idealization, but it serves the purpose of illustrating some of the basic properties which we are looking at. And you can easily see here, if you take the outer product, the inner product between the two different states, that will just be 0. Yeah, actually. And next, after the break, we are going to look at the two important operators. And then you see again the outer product, which translates into a matrix. So this will be the unit matrix. So the unit matrix is the sum over all the states, the outer product of all the states you have. And then you can define an operator which just projects out. So this will actually just project out one state. But it's time to stop here, right? I went a little bit over time, so I would suggest that we just meet in 15 minutes. That means 11:20. And guys, feel free to go to the CCSE, grab some coffee if you want to, or tea or water or whatever, or just chat here. So before the break, we discussed a simple example of what we might call an orthogonal basis. And this basis can then be used to define things like obviously the identity operator, which is given by the outer product of these two states. And that's the definition which you see up there. And you see this ends up as the identity matrix. In principle, these spaces are infinite dimensional ones, unfortunately. But we will always truncate them in one way or the other. And we can then define projection operators like these, which means that when we operate on one of these states, if we have a linear combination, and this is the standard mechanical superposition. So if we take these operators, so let me just switch back to the whiteboard. So the thing is that we have a set of states now, and where you could think of two states which can be measured and observed experimentally. So this could be a state which we call E0. This could be just one particle, or it could be many particles. So we don't need to define that now. So that means that we have a state here, which I called phi 0. So that represents this system. And then I have a new state, which is given or represented by this wave function here. That means that there is a Hamiltonian operator. So H here is the Hamiltonian of the system, which acts on this state phi of I. And it gives us an eigenvalue multiplied with phi of I. Then we have assumed that these basis states are orthogonal and normalized. So since these are the solution of an Hamiltonian problem here, so what we have then is that phi of I and phi j is equal delta ij. Then what we have, if we look at the inner product, so we can always define these states in a specific way. So what you see here is just one way of realizing the state. So we have two possibilities. So we have 1, 0 here. So just a way of setting up a vector, right? There's nothing more than that. And then we have the other one, phi 1, which is equal to 0 and 1. So these are often used to represent spin for particles which have half spin values. So one could represent a spin up state. So later in this course, I will often use a notation where I just write spin up. And then this could be a spin down. So this is a typical realization of a binary system. In principle, however, there is an infinity of states up here. But now we're just looking at an effective Hilbert space, which contains only these two states. One of the first exercises you will see next week deals actually with such a system, a so-called two-level system. And I'm going to call these states for either the basis states or the computational basis. So we have a computational basis, and sometime I will just say basis. Which now contains this phi 0 and phi 1. So this computational basis now is something which I can use to make, through the superposition principle, I can make linear combinations. So I can actually have a new state expressed in terms of these. So I could define a state psi, and I'm going to put a 0 here, which is now given by a linear combination alpha of phi 0 plus beta of phi 1. So this state would also be an eigenstate of the system. One thing which I would like to say now is that in more general terms, is that we can define a specific state. So let's call this phi of I, which is now given in terms of an expansion of a huge orthonormal basis. So we could have a big set of states, j equals 0, and in principle to infinity. In principle, because you would have infinitely many states if you think back to something like the harmonic oscillator or the solution of the hydrogen atom, you have an infinity of states. And this would now have some coefficients, which I'm going to label Cij, multiplied with this basis phi j, and where we have assumed that phi j, again, and phi I is an orthonormal basis. Normally what we end up doing, and I'm putting an approximation sign, is to have a sum which goes from j equals 0 up to some parameter d, where d now represents some kind of effective Hilbert space, or a truncation we make simply because we cannot handle more states. So many of these methods reach a kind of computational limit, which is determined by the mathematical algorithm which you're using. So you would then have an approximation, but where you still have this basis. So this basis which you have can be a chosen basis, which may not necessarily be the solution of the full problem. So you can think of the full problem would be given by a Hamiltonian H, which is not the same as the previous one, and then multiplied with this psi of I, and that gives us an eigenvalue, E of I of psi of I. But what we have then is that this H acting on this basis we have chosen is not necessarily equal to E of J times phi of J. So we are saying that phi of J is not the solution of the full Hamiltonian, but it could be the solution of a separate part of the Hamiltonian. But it's still an orthogonal basis. And if you have an orthogonal basis, you can always expand a new function in terms of that basis. So I'm saying this because I want to give you some of the basic strategies which we end up in many-body physics. So the question is, why this? The basic strategy when you do many-body physics, a pretty common strategy, is to separate the problem in terms of parts you can solve analytically, for example, or easily numerically, and then you obtain a basis. And then you use this basis to expand the exact solution in. So the basic strategy is to find solutions to parts of the problem, is to find solutions, and then preferentially analytical ones, for parts of the problem. So a common strategy is to take the full Hamiltonian H, which we just now leave undefined. And you can split that one in different parts. There could be a part H0. And then I'm just putting up a part HI, where I stands for interaction. So this could be parts of a given force. It could be two electrons interacting by the Coulomb force, or it could be two protons interacting via the strong force. Now, the whole idea now is that this H0 acting on this basis phi j forms an eigenbasis, which we now can solve our problem, which we can solve either analytically or pretty easy numerical. Okay? So that means that I have some eigenvalues, and now I'm going to try to avoid using the same symbols. I'm going to use an epsilon and phi j. So that means that phi j, these states, is an eigenbasis of a part of the problem. Of H0. And it is an ONB. So that means that the problem now is a problem which is orthogonal, gives an orthogonal basis. And this basis is something which we often call the computational basis. This is a pretty common notation in the literature. So when we are going to talk about computational basis, this is a little bit different from what you do when you do quantum computing, where you simply say that these two states, which can be the states of an interacting, complicated many-particle system, now is my computational basis and represents qubit 0 and qubit 1, for instance. But here, we're actually introducing a technicality. And sometimes for a system of, let's say, electrons, what you can see is that the parts of the problem, so if you think of an atom, you can solve one electron interacting with the atomic nucleus. And that gives rise to the classical hydrogen problem in quantum mechanics, and where you have analytical solutions to a one-particle problem. Now we could assume that we have a many-body problem or just a one-particle problem, which we can solve analytically. And that gives us a computational basis, which is handy. So one basis, which you will see being used again and again, is actually the hydrogen type of basis. Or in other fields, if you have particles which are trapped, like these quantum dots, the potential which traps it, the electric field which you set up, looks like a harmonic oscillator. But it's a harmonic oscillator of final depth. The exact harmonic oscillator, just to give you an example of such a basis set. So a typical example is the harmonic oscillator. That is HO, harmonic oscillator. I'm going to use this as a notation, so harmonic oscillator. And I'm going to use the acronym HO. And we know that the harmonic oscillator, if we now look at the one-dimensional case, one dim, that has a Hamiltonian which looks like this H0 for just one particle. So I'm going to translate this one into an, it's not a lead to sign, but it's going to be introduced in terms of a lowercase h. So when I use lowercase letters for operators, that means that this is a one particle operator. So this is a one body. And when I use the uppercase letter, then it's undefined, but it's normally a many-body operator. So in this specific case, the operator would look like something like this, minus h0, h squared, divided by 2m. There's a second derivative, we are just in one dimension, plus the harmonic oscillator potential, where I have some parameter k times x squared. And in this case, the energies are defined by h bar omega, which is the oscillator frequency. So this parameter k is, so k is proportional to the oscillator frequency and the mass of the particle. So this epsilon h here is now given by this number I, plus, so I is a quantum number, plus 1/2. So that's the energy of a harmonic oscillator. And the harmonic oscillator is a very special case in the sense that if you plot it, it looks something like that. So this is the potential. Let's just put it like this. We have 0 here. So this is our potential, 1/2 k times x squared as a function of x. And then I'm just going to put in the energy levels. So this is not on scale as a function of x, but this would be different states. So we have epsilon 0, epsilon 1, epsilon 2, epsilon 3, etc. And the first one here is actually 1/2 h bar omega. This one is equal to 1/2, actually 3/2 h bar omega. And then I have 5/2. So it goes in steps of h bar omega. Now this well here has an infinite set of solutions. Infinite number of states. And the particles can only tunnel through the potential, but they cannot escape it. In real life, what you do in, let's say, solid state physics by applying electric fields is actually that your real life case, real life, let's say in condensed matter physics, is that you have something like this. And then you will have only a limited set of states where the particle is bound in the well. And then the system, if it goes higher up in energy, then it can escape here. Or you can kick out a particle. So the harmonic oscillator has an infinite amount of what we call bound states. They are all orthogonal. The finite realization, so in a field like Bose-Einstein condensation, the way this was done experimentally is by trapping bosons, particles with spin 1, this can be atoms or it can be molecules, in quadrupole electric fields. So a quadrupole field runs like x squared plus y squared in 2 dimensions. And this is a very ingenious way of doing it experimentally. And it led to the Nobel Prize to Paul and Penning in '89. So this technique of setting up electric quadrupole fields was used to trap particles in small regions in space. And then by laser cooling, where you actually cool down by lasers those particles which have the highest velocities, you could then narrow the Gaussian distribution of particles till just some few frequencies. So the system would then, a macroscopic system, would then, instead of having many different velocities when they're trapped, so it's a gas which is trapped into a small region, then these particles could actually be cooled down by lasers to just one or few frequencies or velocities. So you have a system which just collapses to one state. And that is called a Bose-Einstein, is an example of a Bose-Einstein condensation. So it's two very ingenious techniques which have led to a series of Nobel Prizes. The trapping by electric quadrupole fields by Penning and Paul, and then laser cooling, where you actually shoot light on a Gaussian distributions of particles. You're looking at the velocity distribution. And then you target those which have the highest velocity. And they slow down by collisions with photons. So in that case, what you ended up with is a kind of system which looks like that. This is also done in condensed matter physics with quantum dot systems. And in quantum dot systems, one is actually trying to realize systems where you have perhaps 1 or 2 states, and then you can actually use them for candidate systems for making qubits and making quantum mechanical gates. So this is done, for instance, at the MENA lab here at the university. And it's a technique which is widely used in many, many labs where people try to build quantum devices. So it's a very hot technology, which is really, how to say, if you're interested in that as topics for master thesis, that's really to make the devices, or what you might call quantum engineering, is a very hot topic. And what we are going to discuss now are actually idealizations of these kind of systems. So now we assume that what we have is a orthogonal basis, as we said. We have defined a basis which is an eigenbasis of this specific operator. Now, what we know then from the superposition principle, and if you have a complete basis, we know then that with a complete basis, we can actually represent another state in terms of that basis. So suppose now that your real solution to the system goes like e to the minus x times something. You can expand that in a harmonic oscillator basis, which goes like e to the minus x squared. But then you see that if you want to do that, you would need many coefficients here, many terms to achieve that. So how good that basis is, the computational basis, depends on the problem. So you have some basis sets where you will need a huge amount of basis states to represent the full solution to the problem. So what we are going to do now, basically in this course, is actually to start with a computational basis, which is part of the solution of a simpler problem, which we often can solve analytically. We have nice analytical expressions for these states, like a harmonic oscillator is something which is easy to compute. Same with the hydrogen atom, which is just an e to the minus x multiplied with a Laguerre polynomial. And some spherical harmonics. So these are functions which you can just look up and calculate immediately. And in many cases, some expectation values with these functions have simple analytical expressions, which is even better. So you have a computational basis which is relevant for the physical system, and at the same time gives you quantities in your theory which can be calculated either analytically or easily numerically. But then what we end up doing is that we want to use this basis to find this guy, which is the solution of the full problem. So essentially, and this is, I'm saying this because I want to give you the overarching picture. The different many-body methods deal with us trying to find approximations to these coefficients. And you can rephrase that in different ways. So like Yun here is actually doing large-scale diagonalization. So he has a basis which is often the harmonic oscillator for many particles. And then when you diagonalize, you get these coefficients. These are your eigenvectors from the diagonalization. And with those, you can find the solution to the full problem. So that is a many-body method, which is called full configuration interaction theory. So the different approaches we are going to deal with, actually, if you want to take a bird's view on what we are doing, are actually different approximations to that. Because you often start with a computational basis, which is handy and relevant for the right system, for the system you study. So just to summarize, if we look at these cases here, so what we want actually this one, h times psi of I is equal to the eigenvalue multiplied with psi of I. And we are going to calculate this in terms of that basis which we have. So that means that we are going to actually calculate this in terms of H acting on this linear combination of states J of Cij multiplied with our computational basis. Now, these coefficients Cij, they are nothing but the coefficients of a unitary transformation. And so if you have a unitary matrix, these coefficients actually represent the elements of such a matrix, which represents a transformation of your basis. So theCij's are just the overlaps between psi of I and phi j. So this is actually the many-body problem, or a quantum mechanical problem in its essence. It looks extremely simple, but the problem is we don't have psi of I, so we cannot compute C of ij, and we have to find ways of finding it. So essentially all of many-body physics deals with finding different approximations to the Cij coefficients. So this is how to say what we're going to do in a nutshell. Okay? So when I say computational basis, that means that we do have a basis which we have figured out how it works. And now you can see immediately, if I go back to this simple case, suppose now that I have these two states, this example which we looked at. So I have a state phi 0, which is 1, 0. And then I have phi 1, which is 0, 1. If I look at these, I can now define the completeness relation, which is just the identity matrix. So for these two states, I have my completeness. Which I label like this, I. And that is simply the sum from I equals 0 to 1 of these two states, phi of I, phi of I. That's the outer product. And we found that that is simply 1, 0, 0, 1. Then I could now think of us. We already have, we only have two states, but I want only the lowest lying state. So you can define projection operators which just project out specific parts. So suppose now that the exact solution to the full problem is actually given by this linear combination of phi 0 plus beta phi 1. Actually, one of the exercises next week is you having two states, which means that you're going to diagonalize a 2x2 matrix. Very exciting topic. And then you will find these coefficients alpha and beta. And depending on the strength of the interaction, alpha can be very small, or it can be very large. And the strength of the interaction will actually define how big these components are, the kind of mixing you get. You will see that next week in the exercises. So that means that now we could define a projection operator, P, which is given by simply the outer product of phi 0. There's nothing which hinders you doing that. And if you do the algebra, you simply get this. Then, if we now define a new operator, and this is often called the exclusion operator because that's going to label the excluded space. So this could just be the outer product of phi 1. And this simply becomes 0, 0, 0, and 1. So one thing which you will see is that if I take P squared, just take that previous matrix and square it, just multiply it with itself, it should be pretty obvious that you should get 1, 0, 0, which is equal to P itself. This is normally called an idempotent operator. So an operator which squared is equal to itself is that type of operator. You will also see that Q squared is actually going to be equal to Q. It's just you multiply these two matrices with each other, and it should be pretty straightforward to see that. So this is a general property. It's not limited to two states, but it's something you will have for infinitely many states due to the orthogonality of the states. Then you will immediately see that if I multiply P with Q here, that should again give the roundest number you can think of, 0. This has also an important property. These two guys commute due to that. That's very important. And we are going to use that when we are now going to calculate the expectation values of quantum mechanical operators. Another thing you will see is that P plus Q is equal to this completeness or identity operator. We're just summing up these two matrices. Now, these are very important properties which we will use again and again. One reason for that, if we now go back to this state which we have here, and if you think of measurements quantum mechanically, in measurements you're actually projecting out a specific component. So just to give you a kind of teaser when it comes to quantum computing, what you actually do then is that you prepare a state in a superposition. And this is why quantum computing is such a powerful way of looking at problems with huge dimensional spaces, is because you can actually realize or make states which are in a superposition. But when you make a measurement, then you're acting on the system with an operator. And that operator projects out just one component, and that is what you measure. This is back to this kind of famous Schrödinger cat problem, right? So the thing then, if you now look at this state, which we have here, and I act on that with the operator P. So if I take P now, this operator, and act on phi 0, this for this specific simple system is just 1, 0, 0. And this is now multiplied with alpha, 1, 0, plus beta, 0, 1. And it shouldn't come as a surprise that this is simply alpha times 1, 0, which is equal to alpha times phi 0. So what I'm doing now, I'm just projecting out a part of the wave function. So this kind of technique with projecting out specific components is something which we use, for instance, in many-body perturbation theory, where we actually want to define an effective Hilbert space. And then all the other degrees of freedom which in this case, for this specific system, would be represented by this state here. And you're going to see an exercise where you're going to do that. All the other states will be then represented in a perturbative expansion. So many-body perturbation theory is a way where you, term by term in a perturbative expansion, can add contribution by contribution to the final energy. And at the end, you should get the same as if you were to diagonalize this 2x2 problem. And these are exercises which we will see through the semester. Okay? So these are some of the kind of basic overarching things. I invite you to take a look at the slides for this week because there's some more linear algebra. And tomorrow, we are going to look at some more definitions, but now we're going to actually calculate expectation values of a quantum mechanical operator with a wave function for fermions. And then with that, we are going to define more compact quantities, which we will use throughout the course. But this serves as a kind of introduction to what we are going to do and the kind of overarching pictures which I want to have you with me on. So just keep in mind, so what we are doing now is that we are going to define, to repeat, a computational basis, which is often a solution to a simpler problem. And in many fields in physics, like atomic physics, molecular physics, solid state physics, a kind of a single particle problem makes sense because the interaction between the particles is weak. So a large fraction of the energy is often given by the kinetic energy and the energy due to the potential which a single electron sees. So a so-called almost independent particle picture makes sense. And then you can often find a solution to a simpler problem which deals with the motion of just one particle. So these are often called mean field theories. And those of you who have studied density functional theory have already met that. And with that, you can build a more complicated wave function with that basis. Then these methods which we're going to discuss, they actually don't apply to strongly interacting systems. Then you would have to find different strategies. So in the Bose-Einstein condensation of liquid helium, where you have strongly interacting atoms of helium, then this kind of machinery breaks down because you cannot identify an effective mean field. So the methods have their pros and cons and regions of applicability. So one of the other overarching things I want you to take as a takeaway message from this course is actually you having a deeper insight about which methods work in different regimes. As I said again, physics is always about finding the relevant degrees of freedom. Actually, all of science is that. And then the beauty in many of these methods is that you can make a mathematical framework where you link different degrees of freedom. In other cases, you just have to wave your hands and hope for the best. Okay. We'll take a break and then meet again tomorrow. Is that okay? And feel free to ask questions here.